Hello, my dear friends. This is Dr. Mohamed Nezami again, coming to you from Jerash, Jordan. Behind me is the ancient Roman city, Jerash, Pompeii of the East, as they call it. Well, today I'm going to go ahead and continue my video series on the Ka, and Ku band antenna LNB feed structure designs. Okay, so you may recall. Let me just get this made smaller and take it over here. This is my YouTube channel. I urge you all to please visit. You can actually scan this QR code in here to get to the channel. So please visit this channel and sign up and subscribe and share it if you could, please. It would. So today, if you're gonna go to the playlist, I have this playlist in here, which is this one here, and it contains part one and part two and part three of the of this video series. And today we're going to go into part four, okay? So that's what we're going to do. All right. So part four today. This is my email if you'd like to reach out to me. I'm going to soon have most of my slides posted on SlideServe. Not yet, but I will announce that either on my LinkedIn account or on my during my videos. Okay. I'm a freelance RF and microwave circuit designs. If you have any board level designs that you would like to contract out, I urge you to reach out to me. I work very inexpensive, as you can see, because I operate not in the United States or Europe, so I have a very reasonable rate for designing. The first few hours consulting is always free. If you have any product that you would like to develop, if you have a board that has obsolete parts that you would like to upgrade and upgrade, if you have a brand new design, I work with you from concept to specifications to architecture to modeling the architecture, validation of the architecture using CAD systems, and then on to schematics and BCB layout. So I turn in final, I work with you with the BCB house also. I turn in all the fab files. You get Gerber, you get bill of material, you get all the parts off the shelf in a nicely done way. And I work with you. I even go as far as testing and validation on the bench as well. I work with you. So please don't hesitate to reach out to me. Mainly my emphasis in the transmit receive areas. So be it anywhere from DC to 35 gigahertz, we can do it for you, including receivers, transmitters, power amplifiers, synthesizers, low noise amplifiers, and so on. Okay, I have also a training that I hold yearly, a few of them, and the first one is going to be during the last week of April this year, 2025, and the place is basically in Jordan, in my city, Jerash. The course basically is really involves whatever you see in my YouTube channel. In here, all the designs, all these videos that you see in here, um, we go ahead and design all of these. All these designs that you see in here, using HFSS, System View, ADS, Momentum. We do all of these and Cadence, also Allegro, BCB, and schematics and OrCAD schematics. All these we do them basically, and you get a source file for all of these designs. We do them in-house in 1 week, and so you can go ahead and The cost is $2,000, including the hotel and lodges. So I handle your staying and your transportation back and forth to various places. All you have to do is just pay that, and then you pay for your own ticket. The training is also, I could customize this based on your, if you have a company that you have, you can gather up to 5 people, at least minimum of 5 people. I could come in, fly over to your site and conduct this also. So basically, this is hands-on. You come in with your laptop, and on it is your, if you don't own it, evaluation copies of the various CAD systems, the ANSYS HFSS and Keysight ADS, and then we work with you on that. Okay, so let's get back to our topic today. I'm going to go ahead and start resuming part 4 of the series. And as you know, basically we started looking at the LNB to antenna feed structures, which is a niche area that is always critical and very challenging. So I put in here, just grabbed a few pictures of various types of systems and their feeds. So basically, be it like you see in here, where we see the horn, we see a square waveguide feeding an OMT. And the OMT, of course, you get two things. You get one side where the receiver, and you get another side with the transmitter. And this could be a filter in here, might be a filter in here. Same thing is done in here. This is probably for a VSAT terminal. So here's your LNB in here, and here's your horn antenna, and this is an OMT basically, and that's your buck in here. So my interest is about how to get this feed system in here, okay? Same thing, this is a home entertainment TV, KA band or KU band, and same thing, it's what's done inside of here. This is satellite on the move, tactical terminals, but you can see this front end feed system is the same almost as probably this piece in here. Same thing in here. And it could be even large gateways, deep space probe link antennas. Same thing, it applies. Again, I show in here a bunch of these feeds that you can see on the Google. If you Google, you get all various types, hundreds and hundreds of different products and ways of doing so. The LMB itself, I urge you can go back to my channel, and you can see I have the LNAs and KU SATCOM buck converter, for instance, the buck and the LNA. This is low noise receiver front end. So you can get see go to my videos and you will see how we do design these. But I grabbed this off NXP block diagram that describes basically a typical one of these LNBs, like this one in here, for instance. This is for TV systems. So basically, you get a circularly polarized signal that you're receiving from a satellite, which has horizontal and vertical signals. And we amplify these in a low noise amplifier, and then we mix within a load, and then we can get back basically a signal between 950 to 2150 megahertz that we feed into the indoor unit, which is satellite receiver or satellite modem. Of course, incoming signal in this case for a KU band typically is 10.7 to 12.75. So basically, what I'm interested in, what I have been doing, is looking at how do you design this interface between an antenna and the LNB itself. This interface in here is basically what I'm interested in. Now, just to show you, give you an idea, this is the same LNB that block diagram in here. This is the implementation of this with a highly integrated mimic, complete low noise a block down converter that has all the synthesizer. It has basically a reference crystal in here, 25 megahertz that feeds in, and there's a phase lock loop synthesizer inside that generates these hello signals. And the mixers in here and the IF amplifiers are all inside of here. So all you need in this case is this external part in here, which is basically the LNA chain and then the image rejection filter. And that's what you see in here. Here's the image rejection filter, and here's one stage, two stage. These are misfits, and here's the horizontal, and there is the vertical. So basically, we get these two, and pictorially, this is how it's done. Really, you got a horn antenna in here. You've got a square waveguide in here. The square waveguide. There is a little piece in here that you see this bobby part in here. That's the basically circular to square waveguide transition. It's a little small piece. You can literally put square waveguide right against circular waveguide, and you would not get a whole lot of deterioration. But in a lot of cases, it doesn't cost you much to put the interface in there at the transition. And you can see in here, you can see really clearly, you can see where the in this waveguide, there is two probes, one pin probe in here and one pin is right here. And you can see there's two devices in here. These are the two devices in here, the gasfits. Okay, the misfits in here. And there's two hairpin filters that you see, microstrip filters. These are these filters. And there's the IC chip. There is this, and there's the crystal oscillator in here, external crystal. And then, of course, you get two IFs in here. This one here shows that you have four IFs. It's the same way. It's similar. Okay, so basically, with an LNB, that interface usually you get in more professional one, like you see in VSATs. This is what you get basically. There's an OMT that comes in, interfaces to the horn antenna, and then you get a square waveguide like you see in here that interfaces to an OMT, orthogonal mode transmode device, which splits basically the vertical and horizontal separately. And same time, it could isolate the transmit or receive signals if you have transceiver. And what you end up with basically from square wave, okay, interface or circular interface, you end up with two rectangular waveguides, okay? And these two, in this case, one is transmit, one receive, but they could also be uh, um, low noise block down converter. And these are basically in that case, in a case like this, the LNBs would be separate units where you attach them to this one. And you can see from the waveguide TE and TM modes patterns, what we usually dealing with all the times is the TE10 mode, okay? And that's where the aperture, basically, if you look at the aperture, your E field signal is right in the middle, maximum, and it goes like a sine wave, basically, on the left and right hand from the middle of the waveguide. Okay, we have also a case where the TE01, we have an interest in that because when you go to a square wave, you get a circular polarized signal in there, which is basically has these two modes, TE01 and TE10, both at the same time in here, the presence. And in the past series, I dealt with that as well. Okay, here's another look how this LNB is done when you have a circular waveguide. So basically, here's our horn. Here's the transition from the horn to the circular waveguide. And the circular waveguide, we have a board in here, and the board has basically pins. One is right here and one right here, and these pins are going inside the waveguide. One goes to the vertical and one goes to the horizontal. And they pick up the signal and they amplify, and then they come with an IF. And usually the pattern is TE11. Okay. We'll say more about this. Now, in the case of a square waveguide, of course, it's the same way. So basically, this is a square waveguide, and here's the transition from square to the horn to the circular aperture of the circle waveguide that is the end of the way of the horn feed. And this board in here, you can see in here that there's a solar bulb in here, and there's a solar bulb that is in here. And each one of these are actually pins that go down into the waveguide. One goes vertically, and one goes and has a 90-degree bend to pick up the signal, basically both this signal and this signal, because that's basically what you're decomposing the circular polarized signal. And this is again the same one, similar one to the one that this is the same one that I've looked at earlier. In this case, in here, this is highly integrated, just like we showed in here. This has these front-end amplifiers, and there's the mimic down converter chip with the IF amplification. And there's the crystallized device that is used as a part of the reference signal to the phase lock loop inside of the mimic down converter. Another view of this basically on the side. So you can see this here, this part in here, that's where this pin on the side that goes down. It goes down, and this is almost, it goes down here, and then it goes bent internally into the body of the waveguide to pick up the horizontal signal. And this acts like a coaxial line, really. So this is actually two coaxial, two microstrip transitions, one in here and one in here, as you can see. One goes down this way and one goes down and then that way with a 90-degree bend. Now, the LNB feed that I have surveyed over the years, there's a number of them, but I could classify 5 types, and I did pick up a few of these, and these are scattered all over the net in both videos and pictures. So a lot of people did tear down and studied these over the years, so they're available on the net. So basically, we have these types, and depending on whether you have what type of waveguide, whether it be a rectangular waveguide or a circular waveguide or a square waveguide, we can go different types. Okay, so we start out with a type that, for instance, in this case, this one here, there's a rectangular waveguide. This is a probe feeding, and there's, of course, a cover that comes in here, and the cover itself has a compartment that depicts the quarter wave shorted section on top of this. And then this waveguide in here, by the way, there's another feed in here which is using pen. So this is printed probe, but for this polarization. But there is another one that is going down this way for the vertical. This must be getting the horizontal. And of course, the waveguide, you can see that it's coming this way. Okay. Of course, we got one signal comes in here, there's amplifier in here, and there's a T-junction in here, and the other one is coming in here, gets amplified, and of course we go in and we'll talk further on this. Another type that uses this with a septum OMT that I will cover in the next session. Okay, in the previous session we did cover a little bit on this. And then there is another one in here that has for circular waveguide. It has a printed probe in here, but also has a pen in here for the other polarization that is going inside basically and then bent that way. And this one in here, for instance, you can see the coaxial insulator and the center pen for both the vertical and horizontal. This one, what we just showed before, is with the type that is basically uses those 2 pins in here, and we'll talk about. So these are 2, 4, 5 types, and I did list them in here. So let's go ahead and look at these. The first one is rectangular waveguide LNB feed using printed or pin probes. Okay, and we will talk about these. I'll show some samples of this. And today's session, we're going to focus on these feed architectures, feed methods using waveguide to a microstrip transition that we will do today. We'll cover these, and these in here, this one will be another part, and this one will be another part, and this one will be another part in here. So this will, all of these will be modeled and presented to you in the next sessions. So the next one is dual polarization, whether circular or square waveguide, with that uses Septum with the printed probes, and that's this type here. So this is the type that uses Septum polarizer with two probes for the vertical and horizontal. The next one is a dual polarization circular or square waveguide LNB feed using orthogonal printed pen probe without septum, and that's this type here. Okay, and we'll talk about this, that the fact that this is here does not use a septum in here. So we always have vertical and horizontal, where in this case, we might not have both of them at the same time. Well, basically the signal, depending on a right-hand side or left-hand side, you end up with one side of these semicircular compartments that are basically is a rectangular waveguide. And then, of course, we've got dual polarization circular waveguide LNB feed using a mix of orthogonal printed and pin probes. And that's this one here, okay, this type here. So here's one, for instance, you get, this is the printed probe that comes into the waveguide, the circular waveguide. And there's the amplification here and the whole thing. And then there is another one, which is right here, which is a pin soldered. This is a pin soldered that goes down and bends this way so that, and it's exactly at a half wavelength distance from this guy here. Okay. And we'll talk more about this. So we have this piece in here is actually acts as a short, okay, reflector, where the reflector for this one in here is basically the cover, the lid of this, which happens to be a quarter wavelength. So there's a quarter wavelength short that is on top of this, covering this. There's a quarter wavelength from this guy, but then this guy here is actually is a back short end for another pen that is away quarter wavelength away from here. We'll go through these, okay? And of course, you got dual polarization circular waveguide LNB feed using dual coaxial printed orthogonal probes, and that's this one here, okay? Okay. All right, and we'll talk about this. This is where the both probes are on the same planar, in the same plane, where they're not really offsetted from each other. So they both share the same back short. Okay, so let's talk about what we're going to do is we're going to focus on this today, and then we're going to continue with these. So what I'm going to do today is cover the rectangular waveguide LNB feed structure using printed probes. And I've got for you, of course, all the ones that I'm going to talk about. I did design these, so I've got about 9 of these in here to look at. And you can see here is one, for instance, where the probe is actually on a BC board, is sticking into the waveguide. And here's the probe in here, and there's a quarter wavelength section in here, the high impedance section that matches the 50 ohm to the impedance of the probe. Okay, so I have a variety of these that we will talk about today, which I'm going to cover. So sit back and enjoy these. So we're going to talk about these. This is another type. And then this is the one where we have using pen with a cap. Basically, this is coaxial too. So in this case in here, this really helps. This is basically what we would need to implement when we go to this type. This type in here, for instance, where it's actually a pen put into the waveguide. And then, of course, we've got some KUK band stuff, and this is another one, okay, that uses a ridge step impedance transformer from the coax. This is inline. This one type is different from the other ones because it's inline. A lot of times the LNB is fed, it has to be fed on this side. We can't go perpendicular. So this type here, and here's another type that is also inline using microstrip, okay, and step waveguide. And then we'll talk there's another one with the substrate integrated waveguide with step waveguide, hollow waveguide. So we're going to talk about this. The last one in here is the same thing, except it's inline, but it uses a loop. It's a loop that is shorted, an extension from the inner of an SMA on this side is extended and bent and shorted to the bottom of the waveguide. Okay, so that's basically we're going to talk about these today, and in all of these cases, we're going to look at the frequency response and show you how those behave. Okay, so let's out of from the public domain, basically, I grabbed a lot of these devices that people posted, and I did an evaluation of these, sort of looked at them. So we're going to start looking at the first type, which is basically the rectangular waveguide LNB feed structures. Okay, now here's an example. This is a K-band LNB, and this is very straightforward one. Okay, here's the IF in here, and there's the waveguide interface in here, and you can see how they actually put the interface with a probe, and the probe goes to the LNA in here. And these LNAs, I did cover them back in I have another LNB series on K-band LNB designs where I designed a three-stage low noise amplifier using these very same devices that are here. These are NEC devices, or California Eastern Laboratory used to be called. So we've got the LNA in here, three devices in here. There's a filter in here, an image filter, and there's a synthesizer in here with a TCXO and a trim capacitor in here to trim the frequency of the LO. And this comes in here. Of course, there is a device in here that you bring in the LO signal in here, and this is probably very much the same device as here. So this is a gas fit, a fit mixer. Okay, so basically feeding the incoming signal and the LO, and there's the IF section which amplifies the signal and then goes out to the IF port. Same thing now from the indoor unit, we got to get DC over to here. So the DC comes in here, you can see it coming here, and there's a Xeno diode or a protection, limiter protection on the DC section in here. This is DC section. You see a high power resistor in here for some sort, and these two diodes here for reverse polarity protection. And there's a bunch of course, voltage regulators with an inductor, big RF choke. And then there's the probably some kind of negative um, um, voltage maker, because you got to get negative voltage to the gates of these misfits in here. And you can see there's three compartments in here, three feed ways. This is the gate, drain, gate, drain, gate, drain for all of these devices, because you got to power them. Okay. Obviously, this device in here, because it's a mixer, there is no DC supply to it. So probably might have some gate, DC gate, might, I don't know. But you could build a passive mixer. So that's what you see in here. This is an example of a feed structure that is used in rectangular waveguide for KU band. Here's another one. This looks like a KU band could be, or I'm not very sure what frequency, but it's not K. You can see here's the probe that comes in here. Here's a gas fit device, first stage amplification. And here's another one in here. So it looks like, so if this was the same waveguide, because it's alongside the same thing, it's lined up. This waveguide comes this way, and then it has a turn, a bent, a tapered bent that is behind here. Okay, and what you're looking at here is basically looking right into the waveguide with a tapered section. So this one here really is the horizontal, and this is the vertical, probably, or vice versa. It might be. I don't know. It might be vice versa. But this is interesting. So you get two polarization amplified separately, and you go in, and there's stages of amplification further, and there's an image rejection filter. There's a dual Schottky diode mixer in here with a rat race piece in here. And of course, your DROs, these are 80s LNBs. So during those days, they didn't do digital highly QAM references where they needed phase noise and frequency accuracy. So DRO, there is no phase lock loops. But nowadays, these are replaced with a phase lock loop, just like this one in here. This has a phase lock loop. Okay, so the LO comes in here, they turn, this is a dual band, so they turn either this section or this section on. And you can see here's the gas fit in here, gas fit in here, probably the same device, they used it to implement the oscillator. And here's the microstrip resonator that's shorted at this end here. And there's the dielectric disc in here, and here's the dielectric disc. So, and then the IF comes in here, of course, and then it gets amplified and filtered in here and fed to here, okay? And this is just the DC regulation section. Here's another one, okay? And you can see in this one, there's a pin right here, and there's a probe. And you can see the waveguide clearly in here that it's actually the waveguide direction is coming from here, the propagation. And this is a bent. It's a bent end of a waveguide. So this is, you're sticking it right at the waveguide, and the cover in here, of course, the lid for this implements a quarter wavelength short from this probe that I will talk about in a minute. As I introduced in my previous videos, you need this probe in here be a quarter wavelength away from a shorted end, because as you know, a quarter wavelength waveguide suction with shorted end for the probe, it acts like an open. It doesn't load the probe at all, and all the signal bounces back from it. Okay, so you can see that this one goes in here into the waveguide, and this goes this way. So this is going in. These are orthogonal probes. Okay, and each one is amplifying, and then this is amplifying, and then signals getting summed in this T junction here, and you're going into a common amplifier, and then onto an image rejection filter, and onto again a dual Schottky mixer in here, microstrip mixer. And then, of course, the DRO, same thing. And then the IF is somewhere going to the back of the board. I have no idea where it goes. It goes in here. Oh, no, there it is. Okay, there's the IF amplifier. So it goes right this way. Okay. This is an IF, part of the IF filtering scheme in here. And of course, this is a bias control in here. This switches the between the vertical and horizontal and so forth. You can look this up, the Zatex part in here. Okay, another sample for you is this one in here, and I believe this one has two separate waveguides. One is oriented this way, and one is actually perpendicular. Okay, is a 90-degree orthogonal to this. This is perpendicular to this. And you can see the probe in here clearly. You can see the low noise amplifiers in here, low noise amplifiers in here. And you can see that basically the LO in here is being split in a Wilkinson divider in here to this section in here, mixer in here, and there's another mixer in here. And so you could get a common IF, but you can see the LNB feed structure in here. This is a closer look here. Okay, you can see how the probe in here, and you can see the high impedance section between the transistor and the probe. That's quarter wavelength basically that matches this probe impedance, real impedance in here to a real impedance into this device. Okay. All right, so let's start looking at these. Let's implement several of these and um, HFSS, and um, let's look at the performance. What kind of performance can we get, and the complexity of implementing these? And so basically, what I did is I grabbed four of these type of these, and I implemented them on HFSS. And you can find publications that report the analytical analysis of these, the mathematical analysis of all of these. Uh, in my training, I try to have individuals that already covered Maxwell's equations and they know the theory background. So we just get straight forward to the implementation. But these are in here implemented. There's four of them, and they're in one class of systems that I've looked at. And then there is two of them, which is inline. So as you can see, all of these are perpendicular to the propagation path of the waveguide. Okay, so the signal comes in this way, and this one is 90-degree against it. And same thing in here, same thing in here, same thing in here. In a lot of cases, we don't have the luxury of implementing the LNB at a bend, 90-degree bend from the waveguide. And that's when we need something we call inline, meaning it's basically a long line, the propagation path. So the signal comes in here from the antenna and then goes into, in this case, in here, which is the feed point from the LNB is basically a macro strip with a little flare that matches another small section of a dielectric filled waveguide with a taper dielectric, and then a staircase implemented as this is a multi-section impedance transformer, okay? And I did cover these in another video. You can go back to my videos, and I believe I have a video that covers all of these. Like you can see, there's one in here, okay? That's this one, and that's these ones that I will show in a minute. So basically, so these are two, this is a substrate integrated waveguide in here. So you could go this way or this way. Now, depending on the LNA or the filter topology that you're doing, you can go either microstrip or substrate integrated waveguide. And I did implement both of these to show you the trade-offs. Another inline class of LNB feed structures, they use this type where it's not really printed board. They don't do printed board. What they do is they use the coaxial line itself, a coaxial SMA connector, basically, a bulkhead connector that comes in here. And then in this case, I have a 4 stages of staircase extension of the inner conductor that implements basically a transformer match between the waveguide and the center pin. And why we do this is because obviously you know that the waveguide input impedance is really a function of frequency. So if you don't have this, you have just a pin sticking in, you can match it at a certain particular frequency, but then as soon as you move to the left or right of that frequency, you get very deterioration in the insertion loss and in the return loss. So basically what this does, it really has a very broadband behavior to it. And I'll show you in a minute. You're going to see that. Okay, same thing in here. We have an SMA bulkhead in here that comes in, and we extend the center conductor as a loop pickup point. And basically what it does, it comes in here and goes to the floor of the waveguide, okay? And that gets soldered basically, okay? Or you can use conductive glue on there. All right, so what I'm going to do next is let's cover a little bit material on how do we design these basically? How do we so let's just stick first to these ones in here. The principle of this is really simple, okay? So we got a probe that you stick into a waveguide. You know the waveguide, that particular location, what the input impedance to the waveguide. So you put in a probe. The probe has real and imaginary impedance, and what you need to do, you need to match that probe to a 50 ohm impedance, and that's basically the basic theory principle. It really can be illustrated using the classical E-field pattern, for instance, in this case of the TE10 mode, okay? Now realize if you're looking at a waveguide, at the face of the waveguide, what you see is this. So you see an E-field that basically is a half sine wave, a half cycle of a sine wave, where it's maximum right in the middle, and then it decays to either left or right. So you know that to get a probe, you need to be right in the middle of the A dimension of the waveguide, the broad wall side. So we need to be right in the middle. So therefore, all of these that you see in here, you see them in here, they're all really right at the center of the waveguide. Okay, that's one part. The other part, let's look along the side of the waveguide. We know that when we stick in the probe along the waveguide, one end of the waveguide is always short. Okay, so when we look at all of these right now, the way we model them, this is in here, this is open, but it has a signal. I put a wave port in here, but the other side is always short. The other side is always short. The other side of this is basically short, except in this way it has a clearance to this, and this one is short, and this one is short. So now the distances of basically when we're looking at the E field, if you look at the E field distribution along the Z-axis, along the propagation, it has this pattern to it, okay, which is the E or H field. They both have the plus minus sine beta Z, and beta is the propagation factor. That's the 2 pi over lambda. And the Z direction is basically the distance in here. So you can see that it's also sinusoidal. So you start out this way from 0, you go to the negative maximum, and then you go back to Z, across the 0 in here, and then you go to positive, and it acts like this. And you can see that basically the wavelength basically as a function of the distance in here, the pattern of the E field repeats really every half wavelength. So if you look at this from a maximum to maximum, you get full wavelength. For maximum to minimum, you get a half wavelength, so you get this pattern. So we can see that we want to catch the spot where the E field is maximum, and that's either here or here. It doesn't matter. So you can put the probe in here, or you put it on this side. Okay, you still get the same exact. So and this one in here, it happens to be, if you look at the analysis of this, you're going to find out that this distance in here is really a quarter wavelength from this end. From the back short, it's a quarter wave. And if you put the probe in here at a quarter wavelength, the probe, when looking this way, it sees open, because as you recall, the quarter wavelength transformer, from the transmission line equation, if you stick a distance of a transmission line or a waveguide section with a quarter wavelength, that's, if it's short, it's going to be open. If it's open, it's going to be short. Okay, so we can put every multiple of quarter wavelength, we can put the probe. So the probe, again, is in the middle of the broad side on this way, and then at the same time, along the axis of propagation, it has to coincide with the maximum field point, and that's this one in here. And you can see that also from the current distribution on the waveguide, inside the waveguide. At a quarter of a wavelength, that's really coincides with this E field points in here. So you can put it in here or in here. You're going to get a phase shift, 180-degree phase shift, but it doesn't matter to us. The phase is irrelevant in this case. All right. So to summarize, so basically using the topology of a rectangular waveguide, what you're going to need is you're going to need a probe, printed or pin, sticking into the waveguide right in the middle. The length of the probe is really a quarter wavelength because it's a dipole, okay? And the dipole, the length of the dipole is basically the free space wavelength divided by 4, 1/4. Now, this one in the broad side, so you put it right in the middle of the A, okay? And then now alongside, in the longitudinal side, you need to put it at a quarter wavelength, waveguide wavelength, not free space wavelength, away from the short. So that when it looks this way, according to the transmission line impedance in here that you see in here, the input impedance is equal to this one in here, and the beta LF beta here corresponds, if the length in here is a quarter wavelength, if you put a quarter wavelength in here and you simplify this, you end up basically with this equation. This is being reduced to this here. And if you look at this is basically the characteristic impedance squared divided by Z load. So if Z load is 0 in this case, 0, Z0, which is the free space impedance, 120 pi, is going to be divided by 0, which is going to be open. And that's perfect. This is what we want. And this is mathematically, but pictorially, what you really want to do is you want to put the probe at the point where the signal propagating this way, if it goes back this way, if it doesn't get picked up in here, it goes this way, travels quarter wavelength, and it comes back another quarter wavelength. That's a half wavelength. So by the time it bounces back here, it's exactly in phase with this one, and it sums up, and you get maximum increase in the signal, okay? Now, so, and in the design of these probes, we got some fundamental equations that I'm going to put in here. We can, we are capable of going back and deriving all of this from Maxwell's equations, but we don't want to do that. We're here into applying things and not mathematically going into the principles. You can do that yourself. But let's just remind you of certain few things that the cutoff frequency is this equation in here. The wavelength inside the waveguide is this one here. The input impedance of a waveguide is basically this one in here. 377, that's 120 pi. That's basically characteristic impedance of the free space, okay, divided by this. And that's why, as you can see in here, when I said, why do we need a ridge like this, a transformer, or a transformer like this here and like this, that's really because of this equation here, as you can see, is because the impedance is really a function of frequency. It's really depending on how far this from the cutoff frequency. At the cutoff frequency, of course, it's infinite. And then it starts exponentially decaying down as how far it is from the FC. So this impedance is not constant, it varies. Okay, and of course there's another one, which is also we can show that the waveguide impedance is equal to this one here, which is exactly this, except in another form that is proportional to the broad length to the narrow length, okay? And just one thing that you want to be aware of is that if the A and B are equal, they cancel, and you get twice the 377, which is 700 ohm impedance, basically, for a square waveguide, okay? Now, for a shorted waveguide, this is basically the input impedance to this one. It's basically it's an inductive impedance, and it relates to the free space impedance in the waveguide multiplied by this factor in here. Okay, so you can see that what we want in this one here is that we can have this at infinity when this L is lambda over 4. And we'll show that in a minute. Here it is. So here's an example that I grabbed. Somebody posted this on the net as a tutorial. So basically, we have a small waveguide section with a short end, which is basically what's used in here. So what we want to do is we want to compute the, giving the length of this short section in here, we want to compute the input impedance of the waveguide in here. And that's really critical because that's what we need to do to get the match also. So what we have is we have this equation here, of course. So, and then now we have to find what this is, and that's what that is. So we're going to go in here, we're going to ZTE, characteristic impedance, is basically this. In this example here, the cutoff frequency was 6.5 gigahertz and the operating frequency is 10 gigahertz. So we found that is a 500 ohm, okay? And then the propagation factor, 158 radius per meter, was found based on this. So we bring in this and we come into this equation here and we substitute this impedance in here and we substitute this number in here and we get J100, okay? So this is basically the input impedance in a 20 centimeter shorted section of a waveguide at 10 gigahertz, okay? Now, for the probe itself is really simple to do. So we got a probe. Here's the probe, and we got the feed section, okay? And that's basically like this, okay? All of these, let's see. Let me look. Okay, so as you can see in here, there's the probe in here. There's the probe, just the probe itself, just that piece right there, okay? It's a printed probe, okay? And what we have in this case is we have another transmission line in here that is used to match that probe to the 50 ohm in here. Okay, this is a 50, oops, this one here is 50 ohm, okay? It's a feed, and the length of this is arbitrarily in this case. Of course, this length goes to, this is where the LNA, the first section of the LNA, this line in here would be on the examples that I showed you. Let's look at this. That would be this transmission line in here, as you can see, okay? Or in here, we'll call it. This is the transmission line in here, okay? So basically, so now this one here, we can compute the impedance of this, and the impedance looking into the waveguide loading this probe can be computed as well. So, and this is done this way. So this is really a generic. Now, one thing that I forgot to mention is in these here, the probe has to go through a little hole in here, and this hole in here acts as a waveguide also, but it's a very small waveguide, so that the cutoff frequency of this hole in here, of this window covering the broad length of the waveguide, does not leak any signal. Okay, so we're going to show you. Here's another one, for instance. This is smaller. Okay, you can see this cutoff here, this cutoff in the waveguide. We need that one to have a cutoff frequency, assure that the cutoff frequency of this is way above the operating frequency of the waveguide itself, so that this would not excite modes, okay? And that's basically what we have to do and this is an equation that I grabbed from somebody that analyzed this, and he looked at this and said, well, the feed compartment here, the channel that we are putting into the waveguide, the height of the channel and the width of the channel is really now the cutoff frequency of this is proportional to this. So you need to make sure that this is the width of this is wide enough, is narrow enough, wide enough not to interfere with the signal that propagates into the microstrip line. At the same time, it's way above the operating frequency. okay? And so basically, any probe that you can see here, we're going to have a few parts. The first part is the probe itself, and then a high impedance section in here. And why high impedance section is because this is usually is either a quarter wavelength uh, uh, matching a real impedance of the probe to a real impedance of the feed, or it could be just a high impedance and a little inductor to implement to cancel out the capacitance of the probe, okay? Because there is a reactive part to the probe other than the real impedance. And that's usually capacitive because it's open-ended. So we have that. And then we have, of course, another line in here, which is for matching. And then we have a feed. So we have the feed section, a matching section for the between the feed and the probe, and another small piece of um, narrow line, high impedance line, which basically used in a lot of cases. Sometimes you don't see this always. In fact, in the examples that I'm going to show you in these ones in here that I did, and some of them you don't see it. I don't have it because it turns out you don't need it. In this one, I only have this quarter wavelength. I didn't have a high impedance line. Okay, and it's the same thing I believe in these ones, but eventually in the next sessions we're going to see something like that. This is small. This is not a quarter wavelength in here, so this is just a match to that one. So it's not that you're always going to see one, two, three, four sections to a probe feed into a waveguide. You might not see this high impedance in here. You might just see that. Like this one in here. This is generic. So we got the probe. You got a quarter wavelength section that matches the probe to the 50 ohm line. And you've got the equation here, which determines the cutoff frequency. Now, of course, the transmission line, the feed line in here is a microstrip line, and you all know the basically a microstrip line width is computed with this simplified equation here. And this is from the calc function in the ADS. So basically, in this case, in my case, I wanted a Rogers 4003 8 mil height, and it turns out the 50 ohm impedance is 17 mils, and then the quarter wavelength 90-degree quarter wavelength is basically 160, and we will see that dimension all over the places in the designs that I'm going to do. Okay, so let's start out with the first one, which is a Ka. So we're going to do this Ka band in here, okay? So let's look at that first. Okay, so the first example that I want to look at is a Ka-band printed probe transition that is used to feed an LNB. And that's basically this one in here. So I've got a small section of a waveguide. And what I did is we introduced this here. And as you can see, it's perpendicular to this. So I've got a probe and a small section of a transmission line and then a 50 ohm line. And this one in here, the board material is the 4003, Rogers 4003. So let's look at the top in here so we can identify these. So basically, alongside, I'm looking at the waveguide this way. Okay, so basically I've got the back short is basically is the back here shorted of the waveguide, and this waveguide here, I'm basically feeding it the signal. If you look at it, it's on this side in here, as you can see. So okay, basically feeding this, and the probe is basically coming in that way. Okay, so let's look again on the top side so we can see. Okay, so in here, there's the probe itself is basically this piece in here, and the probe feed is that one, and in the middle we have the match section in here, and the waveguide in this case, this waveguide is it's the standard waveguide, which is 10.668 millimeter by 4.318 millimeter, which is WR28. So basically, when you look at this, the design, basically the frequency response is this. Okay, so we can see that this one was designed for the Ka band from 16 to about 22 gigahertz. Okay, and so you can see the return loss is very nice, and then the insertion loss is at most 0.3 dB. That's what we really need because we're, as you recall from my series on low noise amplifier for Ka band, we were able to do 3 stages of an LNA transistor device, low noise amplifier that had a noise figure of 1. So so 0.3 is okay. So that way we can get at most 1.3 below 1.5 dB overall LNB noise figure. Okay, now let's look at further on the other thing I want to look at is the basically the modes. What kind of modes is excited in this waveguide, and just to make sure that I don't have a higher order mode within the frequency of operation of my desired signal. And as you can see, the next higher order mode at M2 is about 27 gigahertz, so which is way above what I want. And that's, you can see if I extended this further, actually you can see it here where it impacts the impedance. So now looking into the probe, you can see the impedances both basically on the input of the waveguide and the input of the probe. And the probe, you can see it's 50 ohm, okay, the real part, of course. And then the rectangular waveguide is about 370 ohm, okay? We can also display the scattering parameter within the frequency response for both input and output. And you can see it's pretty, it hovers over the nice 50 ohm area. Okay, so let's look at the E field. And you can see the E field, how it's behaving. So you can see here's the maximum E field is here and how it's coupling out of this one. So let's do this way here. You can see that how the transition between the waveguide and the line. So we can rotate this way and start seeing how it's done. Okay, and you can see that it comes in and it's nicely comes in as a TE10 mode, and it gradually builds up and it goes to basically to the feed section in this case, which is this one here. So it comes in and it becomes uh, a microstrip line, as you can see it in here. You can see how the E field is distributed within the substrate and right above the substrate. It's okay, TQEM. Let's see what else we can see. We can see it in real time, how this behaves. So we can animate this. Okay, so you can see the wave is coming in here, and it's basically departing in here, okay? And you can see the reflections of the back end in here. So this is the short back, okay? More cool. You can see how the probe end is basically where it picks up the signal, how it's hot on that open end. Okay, so this is for this design in here, it's pretty straightforward. So we don't have a whole lot of things to do in here. Now, the thing that you really want to do is that we know that you can compute the quarter wavelength of the waveguide distance from the back end in here. back short. And then you have, this goes in the middle, of course. And of course, this one is 50 ohm for this substrate. And then the probe in here, you can arbitrarily start. Uh, you don't have to even analytically compute it. You can just basically put same as 50 and then put in the middle a quarter wavelength of a transmission line between them, and then throw it on the optimizer and just let optimizer do it. So basically, that's most of these how I did them. If I don't compute them with the math equation. All right, so let's go to the next one. And the next one in here, I believe this is a 30, this one I did for 35 gigahertz. So it's the same thing, except I did it for 35 gigahertz, and I made it a little bit different. And this one here, I made it's the same way. So I made this wider. Now, doesn't have to be, you don't have to put the width of the substrate to mechanically stabilize the probe like this. You could might as well just make it all complete. Now, of course, when you go to fabrication, this is really, this is conceptually, this is for EM design and modeling, but for mechanically, when you do this, of course, we do it a little different. Okay, so basically in there, we have a waveguide that comes in here, and then this section in here is just a lead. Okay, so it's a little different, but this is done just basically to illustrate, and it will be valid because electrically is the same design, except that one is more suitable for. So this one is for 35 gigahertz, and let's just see. So the ground plane, you can see that it's right here and extends right into the waveguide. You can see, let's go sideways. Okay, so you can see this is the top metal where it has the feed and the match suction and the probe. And the probe, of course, in the back, you don't have anything. You don't have a ground plane for the probe. The probe is just sticking because you do want you want the reflections back, not to have a ground plane. Where the ground in here is actually common to the metal, to the waveguide thickness. Okay, it's actually conductive to the waveguide. Okay, so let's look at the response of this guy in here. So we're gonna go. This is basically what I have. This one here was good from, let's see, from 27 gigahertz to 40 gigahertz. You can see that's really nice response. Okay, and the of course, if you look at the again the higher order modes, we don't see them. And if you look at the E field of this, let's look at the E field pattern on this. Doesn't look I did it, or it's done. Okay, so you can see that just like the other one, of course, it's the same length waveguide I use, but now you can see that there is more half wavelength because it's a higher frequency. So let's look at the this way. No, let's look at the font. Okay, so you can see that of course, the distance from here to here is a half wavelength. And so this one here, if you were to think of this just like that one, half of it will be a quarter wavelength. So if theoretically this probe in here should have been, let me highlight the probe. Okay, there's a probe right there. That probe should have been there right in the middle of this. Of course, we don't really, because we had to tweak this, because that's in theory quarter wavelength, but we have to really tweak it because of the approximations. You're not gonna get close to the theoretical. And of course, the center frequency that I'm using, I offsetted this, but it works well for the band of interest that I have. Okay. Now let's minimize this and let's look at the next one. The next one, I looked at this and I did this this one. Let me see what frequency this was done at. This is for KU band. Okay, so let's look at again on this one. This one is simpler. This one, what I did basically in here, I use a complete. I put the substrate as complete, covered the whole waveguide. Okay, and it's like this is almost like a batch antenna, a square batch, a rectangular batch antenna. So basically just a straight feed line to here. And then I use the width and height. I've added it to get the best return loss without having any additional high impedance lines. And it does work. And this is basically what I got. This is the response. It's pretty nice as well. So let's see the for this one, same thing. It's clear. You can see the higher order modes in here. Okay. Okay, so let's look at the next one. This is a simple one. This is the old coax to microstrip. Okay, and this one is really very simple to do. The only thing about this is it has a cap, and the cap in here, this capacitive cap, basically it broadens the bandwidth, and you can read about that. So basically, let's look at the design of this. It's pretty simple. So we've got, this is the outer shield of the SMA connector, and this is the inner in here. There is the inner pin. Okay, that is here, and there's the polyflon material. The insulator is right here. The insulator comes in and just covers up to the opening of the of the this one here. Okay, and then you've got the disk, and this is pretty simple and a very wide band. Of course, in this case, the board, a BCB would be sitting in here, and then you would have, this would be soldered just like these ones in here. Let me show you back when we're in this. That would be shown just like this, for instance. This is, you see this? That's a pen that is soldered that went inside into a waveguide. Okay? So it would be very much, so the board will be here on top, sitting on top. This is in the back. And let's look at the frequency response of this guy here. You can see it's really nice, between 11.5 in this case to M2 to 14.5 gigahertz. So this would be a perfect one for a buck converter for KU band. All right, so let's look at the E field of this. It'll be an interesting one to see. Okay, so let's look at the okay, so you can see how the E field, look at it, how it's bouncing back from the back end short, and you can see it's the transition between TE10 to TE mode. Okay, so you can see how the E field in the coaxial line is forming in here. Of course, you can see this. Okay. All right. Let's look at the next one. Oh, this one, that's this one. Okay, so this must be, this is another probe one. Wonder what, so another one, you can see clearly the high impedance suction that cancels the capacitor portion of the probe. And let's see what frequency is this. Okay, this is KU band one, and you can see it was tuned really well. That's the effect of the cancellation of the capacitor band. Okay. All right. So let's keep going on this. Oops. Show that one. Okay. I'll come back to this one. Let me just finish. Let's see. Let's look at these first. Okay. So this one is inline, meaning really it's alongside the, it doesn't, this is good because it's, this would serve well for the, these planar antennas, the flat antennas, because this one doesn't stick out 90-degree perpendicular to the waveguide, so it's in line. And the way it works basically is we have a microstrip line that comes in, and then we match, we have a waveguide with hollow sections. This is the waveguide in here. That's the real waveguide. But then we have these sections in here. And these sections, the first one is basically a dielectric filled waveguide. This one in here, you can see the height of this is equal to the height of the dielectric. And then we got two other ones, and these basically will match. This is really to match. There's three section matching in here. The first match, we have to match the microstrip to the dielectric field waveguide in here. And then from the dielectric field waveguide, we have to match to the real waveguide, okay? So it's an interesting one. And you can read about it. There's a lot of people that have analyzed this and put out analysis of this, but it's straightforward also. The way I designed this is first I designed the section that does the microstrip line on a substrate. And then I put one section of this, designed a waveguide filled, dielectric filled waveguide section. And then I put a match, which is basically this, the flared tapered line that will match from the dielectric filled waveguide to the microstrip. Once I do this, then I made a match between this dielectric field to the actual waveguide. And let's look at the response for this. Okay, this was done for the K band. So you can see that it's from 21 gigahertz to 28 gigahertz. Really nice, very nice. And of course, the E field for this is really, looks like I didn't do the E field for this one. Let me do it. So what we want to do is we want to grab the, we're going to do the vacuum and the Rogers material. Select all and plot the E field into these. So plot the E field. Okay, so there we go. So you can see three different medias. We can see the air filled with waveguide, and you can see the dielectric filled waveguide in here, and you can see a table line and a macrostrip line. So there is it's an interesting multimedia transition. Let's animate this so we can get a nice picture of the how it behaves. Okay, so let me see what frequency is this done at. This is at 25 gigahertz. Okay, so you can see here, let me zoom in. So you can see the waves. This is interesting. I'm going the reverse way. I should be going waveguide to macrostrip, but that's fine. Let's pretend like it's for a transmitter. It's a reciprocal, so it should be the same. So you can see how the this is the TQM section here, and then no, that's this one. Okay, so all right. You can see how the signal is flaring out and then into the dielectric field waveguide, and then going through stair-stepped impedance waveguide transformation, and then onto the final waveguide. So I can reverse these, of course, make it into an LNB feed. So let's do field and data sources. So I'm just going to go out N1, that's 1, and that's 0. Because I really like to see it the other way around. Okay, now we're correct. So basically, as you can see, the E field is coming into the waveguide. This is your antenna in here and feeding into this, and you're going into the microstrip line to this end, which feeds the LNB basically. Okay, so it's an interesting device. Let's put the same thing except in substrate integrated waveguide, because some people like these, you know. It's exactly the same one, except I removed the let me So it's the same one as this, except I removed the microstrip and the tapered impedance match section, and then I only had basically a substrate integrated waveguide section, and then the tapered dielectric into the first section of the transformer. So let's see what I did with this. And you can see this was done for 25 gigahertz. And you can see from M1 to M2, 20 to 28. Same frequency, but different. This one is not as great as the other one in terms of the return loss, but that's because I really didn't optimize it the best. So you can go back and really tweak around or to fine tune the length of the section in here, trying to get better impedance. Or you design the transformer, and that's basically the ratios of this to this, the A to B's in here for all of these sections is what determines this. This was designed as a transformer, Chebyshev transformer. And by the way, you can go back to my this video in here. I think I detailed this very thorough in there. So, okay, so let's look at this again. So we got this, we got the of course this is interesting. Watch this. The impedance looking into the substrate integrated waveguide is only 24 ohms. Okay, that's another thing that I forgot to tell you is that when you do this. Now, your characteristic impedance of this at this end here is only 24 ohms because that's the SIW characteristic impedance with these dimensions that I happen to pick up. So if you need to go to 50 ohm, in this case, you would need another transition to go that will take you from substrate integrated waveguide to microstrip, and I have videos that I did that too. So you can see that in my videos in here. There's one video that I did doing all these. Okay, so you can find my video in here. I don't remember the number of that video, but there's a video that I did for substrate integrated waveguide transition to microstrip. But if you're designing a low noise amplifier, you don't have to do that. You don't have to go to 50 ohm. I could just simply start. In fact, it might be better to start with an impedance of 24 ohm input impedance and then work from there. All right, so let's look at the E field for this. Let's look at the E field pattern for this. Okay, this one is more interesting even. Look at this. So you come in, substrate integrate waveguide. By the way, the thing about this is a waveguide to waveguide. This is a printed waveguide to a real waveguide. So you can see the pattern in here. This is a TE mode. And this is also a TE mode. You can see even how neat this is. So unlike the other one in here, this one in here, of course, if you go back to the E field, now you can see this is TQEM versus TE mode in here. This is a little different than this one. That's why a lot of people would rather see a substrate integrated waveguide rather than so you can see in here how interesting the areas where the match between a waveguide start transforming the mode into a full air filled waveguide. You can see from the height in here. Look at how that signal behaves. It's very interesting. Okay. All right, so let's close this. And now let's go to these ones. We still got two more to go, which is these. Now, these are mechanically challenging to make, of course, because you don't have board. In this case, they're inline, but you still have to get to the BC board somehow. Okay, this would be a neat one to do if you were doing if you can afford doing if you can have an SMA or a K connector connected to another K connector LNA, for instance. But if you were to use these, let me go to these. Where are they? Oh, no, this one. Okay. Oh, here's one. Let's start with the other one first. Well, no, we can do this one. So this one, as you can see, Now, the LNB would be sitting on top here, okay? Because this would come in and you don't have an actual connector in here. You could do an air gap and just go into a PC board pin. And that's what we're going to look into when we cover the other ones, these other type of LNBs, like this one here, for instance. This one here, you go from the board with an air gap to the waveguide, actually. And so is the other ones as well. Like, for instance, like this one here, this type. Okay. All right. So let's look at this guy. I put it what this is KU band, I think. So let's look at the frequency response for this one, and you can see that it's not as broadband as the other ones because this is a loop one. It's a challenge to design it. So this one is between 11.2 to 14. That goes. It doesn't match really well with the receive suction, but it needs to be moved back a little bit. All right, so let's for the heck of it again, just like we did the other ones. Let's look at the E field. Where is the E field for the air gap? I didn't. Okay, let me plot that. So let's pick this guy. Select all and disconnect. Plot E field. Okay, so you can see now how the E field is behaving. And you can see that you can animate. Ah, there it is, I have it. Okay, so you can see, look at this. So you can see the TE mode, how it's being converted and picked up pretty hot, how it's picked up by the center pin of this. And let me do this, animate this. All right, here we go. TE mode to coaxial mode. Okay. Of course, this point here is the short point. This is where we're shorting with the body of the waveguide. All right. Okay, so let's go to the ridge one, which is the last one, I believe. That's the basically let's see, the N line one. Oh, well, I lost my way in the slides, but let's go back to this one. Is this one? Is it? No. Ah, okay, there it is. It's this one. So this is very similar to the methodology of doing the stair-stepped waveguide to microstrip, but this one is the stair-steps transformer, impedance transformer match. It's between the center conductor for with the waveguide, okay? And this is also covered in the uh, technical publications. You can go back, go on the IEEE and see it. And this is really nice, really broadband. This is an octave. You can see that this is extremely powerful. This would be a nice piece to do for the laboratory, for the lab to have. And you can see that it's going from M1, which is from 11 gigahertz almost to M2, which is 20 gigahertz. So it's an octave. That's pretty good. And of course, got 50 ohm, 47 ohm almost on the impedance on the other one. The modes on this one, of course, we can only utilize this portion in here. And let's see. So let's look at the E field, how it's behaving on this one. Okay, so this is that. can see how the ridge, let me go and, and let me just point to, let me just highlight the, okay, so you can see how the transformation from T to TQ mode on these. Let's animate this. And this is, let me see what frequency this is at. This is 13 gigahertz. Okay, so let's look at this with different, the size you can see. Okay, let's look at the, okay, so you can see how the, interesting. Okay, all right, so, okay, so ladies and gentlemen, so what we covered today is basically we covered the this type of feed LNB feed structures for rectangular waveguides, basically something similar to this. So we went through first a series of boards just to show how typically it's done, and then I showed four varieties first, which are like these ones. Then I showed two inline ones, one for substrate integrated waveguide, one for with a microstrip to waveguide. And then the other ones, two different mechanical ones from coax to waveguide using either the ridge transformer or the loop. Okay, and the loop was narrowband. This is very broadband. Okay, so and then we showed the principles of the where to place the probe. We know that it's has to be placed in the broad half of the broad dimension, starting out with quarter wave, free space quarter wavelength length probe, and then working, tweaking that with the optimizer. From the back short is always a quarter wavelength distance in theory. And we showed these, and we showed basically all these. Uh, different examples, nine of them. So I showed nine examples of these. And with this now, so we did this with this. I'm really we can go ahead and for instance go ahead and implement one of these ones in here. Like let me show you this, like this one here, for instance. This uses, we've got two feeds, one feed in here pan and one printed. So we can easily do this. But what I'm going to do next is really, I've done this one, so I just need to detail that and make a video for that. I did this one. And then we're going to look at this one because this is very common use in the low cost commercial applications, which was an interesting one. This is a septum based circular waveguide LNB feed. It's the same as the square one as well. So I did this for both. That's what we're going to be looking at next time. Okay, ladies and gentlemen. So this is Dr. Mohamed Nezami again. I would like to uh, thank you again for it's pleasure that you're watching my video. Please go ahead and go to my YouTube channel. Please pay a visit. And if you could please, I would appreciate if you can subscribe and share the channel. It really gives me a nice support when I get people to subscribe. So please do that. Until the next time, I will see you later. I will be posting these slides on my LinkedIn account until I get the the other one, which is the slide serve one done. Okay, that's this one here until I get them loaded on here. Okay, ladies and gentlemen, until then, I thank you very much and have a great day. Thank you, gentlemen. Thank you very much, ladies and gentlemen. Thank you. Have a great day or night, wherever you happen to be. Thank you.